Good morning, all. Today we are covering the lab assignment 2 of our LP4 lab. This lab assignment is on basis of implementing a feed-forward neural network using Keras and TensorFlow. So first we'll read the problem statement. So the problem statement is implement a feed-forward neural network using Keras and TensorFlow to classify handwritten digit images covering the complete deep learning pipeline that is from package setup, data loading, architecture definition, training with the stochastic gradient descent, evaluation, and visualization of a training behavior. So this is all we will be covering, right? So the data set which we will be using in the problem statement is MNIST data set, which is my modified National Institute of Standards and Technology data set. That's the full form of this MNIST word. This particular data set contains 70,000 grayscale images of handwritten digits. The digits are from 0 to 9. In our program, what we will do is we will split it into 60,000 images for training and 10,000 images for testing. The image size for the data set is a fixed, which is 28 into 28 pixels and a single channel. It is a grayscale image. It's not a RGB image. Then each image has a corresponding integer labeled as 0 to 9, indicating the digit it represents. It has the official source for downloading of the dataset. You can search it online. There is a Kaggle mirror also, which is available. For this particular lab, we will be directly accessing the dataset through tensorflow.keras.datasets.mnist. You can see it in the code. Now, why we are going for this MNIST dataset? Because this particular dataset is small, clean, well labeled, and it requires no complex processing, pre-processing, I would say. What does it mean is we don't need to resize the data, or there is no need of color normalization beyond the simple scaling. So this data set is very simple data set. Right. So let's go to the first part, that is the A part of our problem statement. I hope you all are able to see the screen and there is written as A, right, in the screen. So this is what we are covering currently. That is import necessary packages. What we are doing in this import necessary packages, we are first importing NumPy. This NumPy as NP. Again, going back to the basics, NumPy is the numerical computing library, as we all know, and it handles the array operations. Then we have matplotlib.pyplot, which is considered as a PLT. So it is used for plotting the library, aliased PLT, and used to draw a simple images and training graphs. Then we have the TensorFlow, the core deep learning framework. Then there is a Keras. Keras is also getting imported. So it is a high-level API within the TensorFlow for building a neural networks with the minimum code. So again, I will repeat. You can see over here. There is a Keras. Keras is with this, which is imported from the TensorFlow. Fine, and it is a neural network. It's used for building a neural network with minimum code. Then there is a sequential, a model class where the layers are stacked linearly one after the another. We have a dense, a fully connected layer where every neuron connects to all neurons in the previous layer. There is a flatten, which reshapes a multidimensional input into 1D vector. I hope you all are able to see this flatten. This flatten, it's going to reshape the multidimensional input, that is 28 by 28 image, into the 1D vector, that is 784 value. Then we have the SDG, which is my stochastic gradient descent. It is used for optimization algorithm and used to update the weights during the training. Then later there is the MNIST, which gives the direct access to build in MNIST dataset. Then we have this from tensorflow.keras.utils import to categorical, right? So this to categorical converts the integer labels into one hot encoded vectors and required for the categorical cross entropy loss. And then we have, lastly, you must be able to see that the print TensorFlow version, tf dot underscore version underscore. So this attribute holding the install TensorFlow version training. So if we execute this code, see here I execute the code, you can see the output is TensorFlow version 2.20.0. So we have the TensorFlow library version as 2.20.0 over here. Right. Now let's move to the second part. This second part is loading the training and testing data, which is given in our problem solver. So we'll see every line one by one. See here, you can see that this command, these all commands or this code part has been executed in 8 seconds, and it has given the output as TensorFlow version 2.20.0. Now we'll move to the next part, which is my sub part of the problem statement, which is to load the training and testing data set. So here, what we do is first we are having the code as x underscore train, comma y underscore train, comma x underscore test, comma y underscore test, which is equal to MNIST dot load data. So this actually, you can see here, there is a MNIST underscore load data. This particular part, it downloads or it, in fact, we can say it loads the cache with the MNIST data and returns two tuples. Fine. So this, after what it returns, these two tuples. The tuple is training data set and testing data set. Here you are able to see the tuples which is getting returned by it. So it's the training data set and testing data set. Fine. Till the time we'll start executing the code block also along with the explanation. Then we are printing the training data shape. So x train dot shape and y train dot shape. Now x train is 60,000 images and the source shape is 60,000 comma 28 comma 28 because 28 is my image shape. And as we have decided that we will be taking 60,000 training images. Then there is a y train. So y train is again 60,000 integer labels, that is 0 to 9, and the shape is 60,000. Right. And then we have the X test and the Y test. So these are 10,000 test images and the labels and the same structure. This dot shape is a NumPy attribute which reveals array dimension. You can see here there is a dot shape. What does this dot shape do? It reveals the array dimension. So it is used to verify whether it is getting loaded correctly or not. Right. So we'll see the output. I hope the command is executed till now. Yes, it has executed in 1 second of time. You can see here what it is written, downloading the data from this. So it is downloading the data from the storage of the data set, and then there are different things which are displayed here, and then you can see. So here what you say, that download the line runs only on the first execution, right? This downloading line is runs on in the first execution, the cast afterward. Then there it says that 60,000 comma 28 comma 28 confirms the 60,000 images, each of the size 28 by 28. Right. So the training data shape is returned. And then see, and then even the testing data shape is also returned, which is 10,000 comma 28 by 28. Now verifying this shape is very critical because a mismatch can cause the accidental slicing or reshaping the earlier would cause every downstream layer to fail with the dimension error. So we require the confirmation of the shape at the start moment. Now after this, we have the next part as, see, I hope you are able to see this output. Over here, we have the output as 0, 4, 1, 9. So these are the handwritten digits and its labels are also given to us. Right. Now we'll see what does this code do. Right. So the first we'll see the explanation of this xtrain is equal to xtrain.as type float 32 divided by 255. This dot as type float 32 converts the pixel values, originally integers, that is my 0 to 255, into floating point, which is required for the network computation. And then we do the division with 255.0, which helps us to normalize. It helps us to rescale the pixel values into the range of 0 to 1. Uh, as we know that neural network trains via the gradient based optimization. So the large unscaled input causes the unstable or the slow gradient updates. So the normalizing pixel intensity is the standard practice and directly improves the training stability and convergence speed. And so we require the normalization. Fine. Then after this, we have the one hot encode labels. And where I do the y underscore train cat, which is my categorical, is equal to two categorical y underscore train 10. Let's see what does this mean. Right? It converts each integer label into one hot vector of the length 10. So, for example, the level 7 will be converted into the vector of length 10, which will be like 0, comma 0, comma 0, comma 0, and 1, 0, 0 at the end. So that represents the 7, and then the remaining values are appended with 0, width of the length 10. And so we have the comma 10 over here. So again, I would repeat, what does this line do? It converts each integer label into one hot vector of length 10. Now the question comes, why do we do this? Correct. So the categorical cross entropy loss expects the softmax output layer's probability distribution to be compared against a one hot vector and not against the raw integer. So this makes the label format compatible with the network's output, and thus we require this to convert to this one hot vector format. Then next we have the code of visualize a few sample images. So you can see this visualization which we have seen over here, which is through the this particular part of code. This is very easy to explain, but still I will again like to tell you all small functions from this. So we have the plt.figure, and which is my, and then taking the figure input as a fixed size with equal to 8 comma 4. So this creates a new canvas 8 comma 4 inches. Then there is a plot dot subplot 2 comma 5 comma I plus 1, which arranges the plots into two row into 5 column grid. Plus and which is then 1 I plus 1 because subplot indexing starts at 1. Then we have this I am show with x comma train and the c map gray. This means that they display the image array and the c map gray renders it in the gray scale. Then we have the title, so which captions each image with its true label. So you can see here we are able to see the true label of every image, that is label 5, label 0, etc. Then the plot axis is, we have done it as off, which hides the axis sticks for the cleaner display. Then there is a tight layout, so auto adjusts the spacing to prevent the overlapping. And then we have the plot dot show, which actually renders the figure. And so as the output, we are able to see 2 into 5 grid of a grayscale digital images, each caption with its true label. I hope you are able to see this output over here. This is a visual sanity check confirming that the image data and the labels are correctly aligned and catching any silent misalignment also. And so this, so we require this type of the cross verification to confirm about the data and its content. Then the third part of the problem statement. Fine. So till now we have covered the two parts of the problem statement. First part is the import the necessary packages. We have seen all this, and then loading the training and testing data. Now let's move to the third part. The third part is define the network architecture using Keras. Right. So let us see what we are supposed to do in this particular part. Here we have the code, and then the first part we are doing over here is the model equal to sequential, correct? And then we do the flatten. Now, what does this flatten do? Flatten has the input as the input underscore shape, which is equal to 28 by 28. So this converts 28 by 28 image into 784 length vector. So input shape, from this, the input shape specifies the shape of one input sample. So required only on the first layer. Then the second statement you can see here is the dense 128 comma activation equal to value. So hidden layer is 1 comma 128 neurons. So over here, what we have is 128 is equal to number of neurons, fine. So this 128 is my number of neurons. Then there is a ReLU, which is my rectified linear unit, which outputs the max 0, comma x, and thus it is able to introduce the non-linearity in RK. Then later on we have dense 64 comma activation ReLU. So it's my hidden layer 2 with the 64 neurons. It actually it's called as a narrower layer that learns the higher level, more abstract features combinations. Then I have the dense 10 comma activation softmax, which is my output layer. That is my 10 neurons, and so 1 neuron per digit class. And the softmax converts raw outputs into a probability distribution summing to 1. So this is what we are doing in the code. Right. Now let us execute the code and understand the meaning of output. So here you are able to see the output, correct? Over here you can see the model is my sequential model, fine. And I'm getting the output for the flatten, dense, dense -1, and dense 1 layer, dense 2 layer, correct? So what does it do? So see, there is a flatten with the 0 parameters. Correct. You can see in the output, the flatten is with the 0 parameters here. So this particular 0 parameters, so it only reshapes the data. It learns nothing in this phase. It just reshapes, it just make it a flatten. Then we have the dense 128. So I have the 784 inputs into 128 neurons, correct? So plus 128 biases in this case. So which is equal to 1,40,480. Correct. The answer is 1,480. So this is my dense 128 layer. I hope you are able to see here. That is my dense 128 layer, which is my 1,480. Why this 1,480 has come? Because in the previous case, we have flattened. And so we have got the 784 as an input into 128 neurons plus 128 biases, which gives the answer as 1,480. Then we have dense 64, which is my 128 into 64 plus 64, which is equal to 8,256, as we can see in the screen. Then we have dense 10, which is my 64 into 10 plus 10, which is equal to 650. So total, as a total, we have, here you can see, as a total, we have 1,09,386 parameters. Total parameters are this much, and then they all are the trainable parameters, correct? The number of value SDG will adjust during the training. So this builds the intuition for model capacity. So more parameters can capture more complex patterns. But again, there is always a risk of overfitting. So require more compute data also. So then the learning each output shape represents the back dimension. So it left the flexible until the training and the reference time. Right. So that's the third step of my code. So that was my defining the network architecture. So here I was able to define the network architecture by flattening and then with the 3 dense layer, out of which the 2 are hidden layer and the last one is the output layer. The fourth step is to train the model. Here you are able to see the D is my train the model using SDG. Now let's see what we are doing in this training the model using SDG. So I hope you all are able to see the code. We'll execute also with simultaneously. So here we'll see the line one by one. The first line, it says the SDG learning rate, which is equal to 0.01, comma, momentum, which is equal to 0.9. Right? So this learning rate controls the step size of each weight update. Right? So this rate is going to control the step size. Right? So if I have the too high learning rate, then it is unstable. If I have too low learning rate, then it is slow learning. Correct? And then the momentum also gets added, the 90% of the previous update direction, to accelerate the convergence and help the escape shallow the local minima. So this is what is happening with the SDG. Then I have the model.compile. So this configures the model for training. Then here we have used the optimizer as SDG, which defines the update rule. Then I have the loss is equal to categorical cross entropy, which measures how far predicted probabilities are from the true one hot label. So this is going to define the loss to me. And and then I have the metric as the accuracy, correct? Then this model compile. So metric is accuracy, which is tracked for reporting purpose, and it is not at all used in the pet updates. Then in the second part, we have the history, which is equal to model fit. So here it starts training the loop. Fine. When I have the model fit, it starts training the loop. Now, how does it train the loops? I have few inputs. So first I have the X train, Y train underscore categorical. So training the inputs and one hot label. Then I have the validation data, which is my X underscore test, Y underscore test underscore categorical. So evaluated after every epoch to monitor generalization, not used for the weight updates. Then later I have the epochs, which is equal to 10. So it means that number of full passes through entire training data set. We have the batch size, which is equal to 128. So the number of samples processed before each weight update. So mini batch gradient descent. Then there is a verbose, which is set to 1, which displays the live progress bar per epoch. You are able to see this live progress bar. And then I have the history, which says the objects that store the loss accuracy values for the each epoch used later for the plotting. Right. Now, this is our code. I hope you all have understood the training, how the model is trained using SDG, and where does actually the model start executing, or you can say where the building block of model start. Now over here, we are able to see the output for every epoch. You can see there are 10 epochs. See, here are 10 epochs, correct? So because we have given the input as epoch is equal to 10. Then we have the size of data set, and then it has said like all the data which has been displayed. Now let's see what does this output say. So 169 by 169, which is 469 by 469, which is the number of mini batches processed per epoch. So 60,000 images in total we have. So 60,000 divided by 128 batch size, right? We have seen the batch size parameter, which is given in the training model function. So which is equal to 469. And so we have this 469 by 469 mini batches processed per epoch. There is a loss. You can see the loss is 0.7215, which is equal to to 0.1523. So this is my training loss steadily decreasing, confirms my SDG successfully minimizing the cross entropy error, and the network is learning. I have the accuracy, which is growing in epoch, every epoch you can see. The accuracy is growing from 0.8028 to 0.9563, which is my training accuracy. Climbing means the model correctly classifies an increasing proportion of the training images. Then there is a val underscore loss and then val underscore accuracy are computed on the unseen test set after each epoch. So these numbers matters most for judging real world performance. So over here, you can see that loss is getting decreased and the accuracy is also getting increased, the val accuracy and val loss. You can see that there is a close gap between the accuracy and the val accuracy, that is validation accuracy, which indicates the model generalizes well and it is not a overfitting. So if validation accuracy had plateaued or dropped while training, the accuracy kept climbing, that would signal the overfitting, right? So when you have the validation accuracy and the plotted accuracy same, then it means that the model is generalized well and there is no overfitting. Please remember. And if this validation accuracy is dropped while training accuracy kept climbing, then there is a, like you can say, the alarm of overfitting. So this was all about my B part of T, that is my training the model set. I hope you all are clear with this. Is there any question? I hope you all are clear with this and there are no questions. And so we will move ahead and we will move to the next part, that is my evaluation of a network. See, we have built the network, we have built the model, but now the part which we required is to evaluate the network, right? And so we'll move to this evaluation of a network currently, and let's see what does it do. So over here, I have this test loss, comma, test accuracy, which is equal to model evaluate X test, comma, Y test underscore category, comma, verbose, right? So here I give the test loss, which is printed, and the test accuracy is also printed. Now let's see what this model evaluate do. I hope you are able to see this model evaluate. So let's see what does this model evaluate do. So it runs the training model on the test data and returns the final loss and accuracy. This verbose zero, which suppresses the progress bar output, and then let us execute this part of code also. So it suppresses the progress bar output and dot 4f. I hope you all are able to see this dot 4f in the print statement. So this dot 4f, it formats each float to 4 decimal places for clean display. So this is how I'm trying to evaluate the network. So over here, if you see, there is the output, correct? And the output of this test loss and the test accuracy. So my test loss answer is 0.0899 and test accuracy answer is 0.9726. I hope you all are able to see this. Now, what does it mean? So this is the model's final summary performance. It is measured, computed once after training is completed and on data that never directly influence the weight output. So this is my test data, which is a separate data, which has never influenced the weight updates. So caveat worth mentioning to us is like, since X underscore test was also passed as the validation data during fit, it was simply observed epoch to epoch in the rigorous practice, correct? A separate held out test splits distinct from the validation set used during the training. And it avoids the this subtle information leakage also. I hope you are able to see this. So this is how I'm trying to evaluate my network. Now the next part is we will see the prediction part. So there is a sample prediction here, and we will check the prediction part also. So let's go through the code of this prediction. So here I hope you all are able to see that we have the model.predict. So it returns for each image an array of 10 probabilities, the softmax output. So np.argmax, which is my predictions, comma access, which is equal to 1. So it finds the index 0 to 9 of the highest probability. Correct? There is this np.argmax, which actually do the index predictions of index from 0 to 9 of the highest probability in each row. That is the model's predicted class. So to the output, you all can see the output over here. This is the output which says that the predicted label 72104 and the actual labels is also 72104. So there is a perfect match here, of course, because I think you are able to see the output correctly. So here a perfect match we have got. That is the good qualitative spot check, of course. So with 95% above overall accuracy, the occasional mismatch are also expected in the larger samples. Right. So this is how we are evaluating the network. I hope this part is clear with all of you. This was my evaluation of network. So I do the evaluation with the test data set, and then I do the prediction part after the evaluation part. The next part is my plotting the training loss and the accuracy. So the next part is plotting the training loss and accuracy. So we'll see it one by one, what we do in the training plot and the accuracy. So over here, we are just plotting. It means that we are generating the graph. The first part you are able to see here is the PLT dot figure. I hope you are able to see this PLT dot figure, and which is my fixed size, which is equal to 12 comma 5. Fine. So it creates a wide canvas to fit the two side by side plots. So then I have the PLT dot subplot 1 comma 2 comma 1 by plot dot subplot 1 comma 2 comma 2. So it positions the loss plot on the left and the accuracy plot on the right. So we required the two plots. So one row and two columns. So these are the two plots which will be getting. So we are making the space, we are making the canvas to print the plots. Then we have history, a dictionary storing list of the metric values and recorded per epoch. Correct. Then we have the PLT dot plot and the something dot label, comma label. So this particular draws each line graph and label names the line for the legend. Then there is a PLT dot title, PLT dot X label, PLT dot Y label, so standard X axis and title labeling. Then we have the legend, PLT dot legend displays which line corresponds to which level. Then there is a save figure, which with the parameters as training underscore plot dot png, comma DPI equal to 150, which saves the figure as PNG, DPI is equal to 150. So sets the resolution. So higher, which is equal to higher equal to sharper and larger file. Then we have this PLT dot show, which renders the both plots in the output. So here we have the two side-by-side line graphs. So we have these loss curves declining on the left and accuracy curves rising on the right. Let's see the output over here. Here. So we have the model loss and we have the model accuracy. I hope you all are able to see this as the output, correct? Now we'll see what does this output says. The first important part is we should be able to read the output, correct? Now you can see that the both curves, both loss curves decline smoothly and converge, right? There are two loss curves, model loss, one is blue color, another is orange color. So both these loss curves are declining and declining smoothly and they converge. So what does it mean is model is learning effectively and training is getting stable, right? Then you can see that both accuracy curves are rising and getting converged. It means that the model generalizes well to unseen data. Then we have this validation loss or the accuracy tracks closely with the training. You can see there is a training and there is a validation. The blue one is a training and the orange one is the validation part. So there is no significant overfitting. A healthy model is built through this. Then you can see again the validation loss is rises while the training loss keeps on failing. Falling, correct? You can see here in the graph of the model loss, the validation loss is rising, but the blue colored, which is my training loss, it is keep on falling, correct? So what does it says is model memorizing the learning data rather than learning a generalizable pattern. So if it is happening too much, then it is overfitting. And if both the curves plateau nearly at each poor accuracy, correct? Both the curves with the poor accuracy, then you should interpret as model is underfitted. That is, model is too simple and learning rate is too low or very few curves. So this is what we should learn from the graph. So in our case, our model is very healthy model because both are in the increasing manner, both validation accuracy and training accuracy. And if you look at the this loss, then both are the validation loss and the training loss are in parallel and they are converging. So this is we can see that the pair of graphs which is actually a diagnostic tool in the case of deep learning experiment. So it is very important to read them correctly. And the graphs are informative They are saying a lot to us, but sometimes we are not able to interpret them. So here the interpretability is very much important in the case of the graph reading. So this was our first assignment, first implementation assignment, which is just creating the feed forward network. Is there any question? Is there any question in this? And one part I would like to say to you is, see, if you are using, see, in the problem statement, it is given to use the CIFAR 10 also. So CIFAR 10 is having 60,000 32 into 32 color images across 10 classes. That those are like airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, anything. And you can get the data set from the Kena. And the important part you require is you to import this data set, and then the input shape becomes 32 by 32 by 3. And white and white are already shipped with n minus 1. Correct? Because it is the color images, so you have the 3 channels over here. So with this, our problem statement, implementation of our problem statement is over. The implementation was consisting of feed-forward network using Keras and TensorFlow and classifying the handwritten data set digits, handwritten digit data set, which is covering the complete pipeline by package setup, data loading, architecture definition, training with the stochastic gradient descent, evaluation, and visualization of training behavior. So this was all about implementing a feed-forward neural network using Keras and TensorFlow. Our lab assignment 2.